Okay, those of you in the audience that know me know that I don't use computers, so I'm going to use the blackboard, and I hope that you will still be able to follow something old-fashioned like that. So let's see how it's going to work. By the way, Lev, how much time do I have?
It was supposed to be 40 minutes. You'll still have 40 minutes.
Okay, we'll see. Now, this is the last talk of this beautiful conference. I'm very excited by it. Not by the talk, but by the conference. So I will start it with a light note. I will tell you a little bit how the history of the effect is, but especially I will tell you about two interesting meetings that I had with famous physicists connected with my thesis. And after that, I will discuss the dynamical aspects of the AB effect. So first of all, when I was a student at the Technion, I was very fortunate to hear a class of quantum mechanics by Nathan Rosen. Nathan Rosen was one of the three famous authors of the article of EPR, Einstein-Podolsky-Rosen. And at the end of this class, I think it was the third year of the Technion, each one of us was supposed to write some kind of work, final work, to get a mark for the prize, for the class. And each one of us had to come to Professor Rosen and to discuss with him what topic he wants to work on. So I came to him and I told him that I'm interested in working on foundation questions. So I had some ideas about some problems in measurement theory and relativity. He looks at me and said, look, these kind of questions are only for all people like me. You should not waste your time on foundation questions. You should just try to do some work that is related to real questions in physics. And foundations are really just a philosophical question. And I told him, look, I decided to do physics just because I was interested in foundations, so I insisted I want to do that. And he insisted that he doesn't want me to do that. So we had an impasse. And then luckily, just at this instant of time, David Bohm appeared in the Technion, and somebody told me, go and talk to this professor, maybe he will save you. So I came and met with David Bohm. I told him my ideas. He said, beautiful, let's write an article about it. And that's how we started the interaction. Then David Bohm went to Bristol, and he took me and another student, Gideon Carmi, with him to Bristol University. And that's where I did my PhD. And let me tell you, first of all, how did I find the initial idea about the AB effect? That is because I did not know anything about gauge invariant. I was very, very, actually, uneducated in physics. So I was very excited about Bloch wave functions. And I knew that if you take a periodic function in position, you get nice bends in energy because of the possibility of having two different momentum for the same energy. But I did not realize that. I just knew that if you change position to time, and you can change momentum to energy. So I said, I will have potentials that are just periodic functions of time, and then I will have bends in momentum instead of in energy. And there was something interesting about this idea. If you look at the relativistic Dirac equation, indeed, for a given momentum, you have two energy states when you have a periodic potential. So you can get something in relativistic theory. And nobody has done that, by the way, so that's interesting by itself. But I was using non-relativistic physics, and therefore I put just I solved Schrödinger equation with time-dependent potential, and of course I got just a phase. And it was very frustrating to me that I did not get something interesting. And I remember that I got one morning, and I said, but if I have two different regions of space, and in one of them I have one time-dependent potential, just a phase, but in another one I will have another time-dependent potential, it will be another phase, then maybe there will be some effect connected with that. And that's how the whole thing started. By the way, when I say the whole thing started, I remember suddenly a British joke. I hope you will enjoy it. There is a guy enters into a pub, and he sees somebody standing there with a frog attached firmly to his head. He said, what's going on here? And the frog answered, it all started from a small scratch in my stomach. So it all started from this business of me not knowing about gauge invariance. And I came and told Bohm about it, and he got excited. And for a while, we were just discussing this as an interesting question in measurement theory, not yet connecting it with the vector potential. And then I went to a summer class in Oxford, I believe. At that time, dispersion relations were still fashionable. Unfortunately, I hated it. But anyhow, I had to go and hear how people discuss dispersion relations. And somebody was discussing scattering not by regular potential, by vector potential. And then it suddenly occurred to me that maybe we can have a counterpart to the thing that I discussed in the scalar potential with the vector potential. I came back to Bohm, and we discussed it, and we saw how to do that. And then he said, okay, that begins to be really interesting. We should publish an article, but after you are able to solve the problem of scattering from a line of flux. And I started to work on that, and I realized I have to sum up an infinite series of Bessel functions of fractional orders. I looked at Watson, and it was not there, so I was desperate. And then the chairman of the physics department there, Price, saw that I'm walking around and I'm nervous. He asked, what's going on? I told him, he said, I think there could be a differential equation. If you look at that thing, maybe you can solve it. He gave me the idea, and I did solve it. And then I suggested to him that there will be a course on this article. He said, no, it's not enough. You've published it just with Bohm. So we published this article, and that was part of my thesis, and that's connected with the first thing I want to tell you. At the end of this, when I finished my thesis, you need to have an external examiner coming to check you to see if you are deserving a PhD. And part of my thesis was connected with an uncertainty relation between energy and time. And I gave in that thesis the correct interpretation for it. But it was against what at that time was the fashionable idea that, in fact, the uncertainty between energy and time means that if you try to measure the energy in too short a time, you can't do that. And Price was the chairman of the physics department, remembered that there was an article by Landau and Peierls in which they tried to explain why people had infinities in field theory. At that time, there was not yet the whole renormalization solution. And in that thing, they've used the interpretation of delta E, delta T, which I said was wrong. So Price decided that he will invite Peierls to be my external examiner. Rudolf Peierls was the most distinguished physicist in England at that time, after Dirac went to the United States. And I heard about it. Of course, I was extremely nervous. How it come to be tested by Price was also very good. And Peierls and Bohm wasn't allowed to be in the room, so nobody will defend me. So I'm coming this Saturday afternoon for my oral examination. And Peierls tells me, look, obviously what you did in this part of the thesis is wrong. But I must tell you that I sat together with Price the whole morning, and we could not find a mistake in it. So based on that, and also that we like what you've done with the electromagnetic field and the other things, we'll give you your PhD. But remember, you should be sure not to publish anything about it because it must be wrong. So 3 weeks later, I get a call from an assistant of Peierls. Peierls was at that time the chairman of the Birmingham University. The assistant was called Stanley Mandelstam, was a famous physicist later related to dispersion relations, etc. And Stanley calls me, look, the old man wants to see you immediately here. He wants to continue to discuss with you this issue. So I said, of course, if he calls, I will go. So I went to Bristol, and we spent maybe a whole week, from morning to evening, having discussions all the time. And finally, Professor Peierls told me, look, I think I agree with you now. But that's not the end of the story. 10 years later, here in Tel Aviv, there was something that commemorates the birthday of Landau. Landau was still alive, but it was after his accident, so he did not come here. But there was an international conference. I'm walking in the corridor, and suddenly this man comes in front and says to me, you're young Aharonov. I say, you're a young man, you're Aharonov. I said, yes. This was Peierls. He said, I don't believe you again. And, and unfortunately, I did not meet him after that before he died, so he died with the wrong idea, because obviously everybody now agrees that what I said was correct. that was one interesting meeting that I want to tell you on the light side. And before I come to the main part of my talk, I will tell you about one other interesting meeting that happened while I was still a graduate student. David Bohm was invited to come to Copenhagen to meet with Niels Bohr and other people there, and he told me that he would like me to come also. So I came with him to Copenhagen, and I met there the assistant of Niels Bohr, Or Petersen. Unfortunately, he died. He had Parkinson's disease later. But anyhow, at that time, he was still okay. And I told him that he asked me what I am doing, and I said that part of what I'm worried about is the following thing, that if you try to measure momentum very quickly, you have to introduce very fast change in the uncertainty in position, because you reduce the uncertainty momentum, you have to increase the uncertainty in position, and you can't do it faster than light. That means that you can't measure the momentum very quickly. There must be some limit, minimum time in which you can do it, and that is not reflected in the way that the formalism is, because the formalism allows you to write a given momentum at a given time. So I told him there is a problem, and he said, oh, I think it's interesting, so I will ask Niels Bohr to meet with you. Fine, so I was very excited I'm going to meet the great guy, and there was a meeting arranged, a small room, a blackboard, a table. Here is Niels Bohr, here I am, and the audience was just two people, Bohm and O. Petersen. And I say, Professor Bohr, I would like to tell you some ideas that I have, some questions I have about relativistic theory with measurement theory. He looks at me and said, yes, let me tell you something. And he started to give me a lecture that lasted a whole hour of all the things that I knew by heart about measurement theory and what he has done with Rosenfeld. And then he said, that was a very interesting conversation, and got up and left. So I was completely flabbergasted. I went out. I even did not talk to Bohm, and I just went out of the door, and people meet me at the corner and say, what happened? What happened? So I told them what happened and said, relax, you're in good company. A few years ago, Richard Feynman came to talk to Niels Bohr about the Feynman path integral. And the minute he told him, I'm going to do something with passes in quantum mechanics, Bohr gave him a lecture for a whole hour why he shouldn't do that, and then he left the room and said that was a very interesting conversation. So I felt that I'm in good company. Okay, that's the end of the light notes, and now I want to tell you a little bit, time that is left, what I think is very interesting aspects of topological effects that you can find out there interesting dynamics too, that is an extended of the usual local dynamics that we are familiar with in classical physics. What characterizes dynamics is the fact that when you have, for example, two systems colliding with each other, and due to the collision there is exchange of conserved quantities. So the question is whether we can describe the same idea also when you have an interaction between, say, a solenoid and an electron that doesn't involve at all forces but only topological effects. So let me show you how I came to the idea how to do that, and of course let's start with a paradox, because always when I find something new it first starts with a paradox. So let me show you the paradox that I invented. Suppose you have a grating with a distance L between the slits, and you send here a charged particle, say an electron, that comes in this direction. Let's call this direction X and this direction Y. So the electron initially had no momentum in the Y direction, and then we know that when it goes through this periodic structure, it can come out with some quantized directions, and we can find out what these directions are by Huygens principle, for example. If we take here the difference in the optical distance between this one and the next ray, it has to be integer number times the wavelength, and this is L. So we know that n lambda over L is equal to sine of this angle theta. Now, let's take here the total momentum of the particle, because the total momentum of the particle is not changed since the energy is conserved. That thing is very heavy. It can only give momentum to the electron, but no energy. So we know that the momentum here is exactly equal to the initial momentum here. and we complete here a triangle, this angle is equal to that angle. This is the new momentum in the y direction, delta py. So we find that delta py divided by p is equal to sine theta, and therefore to n lambda divided by L. And we multiply by L here, multiply by p here, and we find that delta py is equal to an integer times h over L. And that's a well-known thing, that if you have a periodic function in the y direction, it can change the momentum in the y direction only by integer times h over L. Now comes the paradox. I put behind each one of these things a solenoid. So there is an array of solenoids, and let's, for simplicity, assume that each solenoid carries exactly half a fluxon. And to make sure that the electron never touches the electron, the solenoid, I can even put protections here, barriers that will certainly protect the solenoid, so the electron could never touch the solenoid. So now what happens? Because we know that each wave that comes, if we take any two waves, one here and one here, there is an extra relative phase between them, which is equal to pi. So that means that now the direction in which the electron can go must change, so that the distance, the optical difference in the distance, is n plus half times lambda, because that extra half lambda has to cancel the change in phase because of the solenoid, so that I will have constructive interference in this new direction. That means that the change in momentum, delta py, with the solenoid is equal to some integer plus half times h over L. Now we have conservation of momentum for the three systems. There is electron, an array of solenoids, and the grating. So if the change in the momentum of the electron is equal to n plus half h over L, and the change of momentum due to the grating can be only integer times h over L, so the solenoid must at least absorb plus or minus half h over L from the electron. Remember, this thing happens with no force at all. So there is an exchange of at least plus or minus half h over L when the electron goes by. That is no problem, because the uncertainty in the momentum of the solenoid is larger than h over L, because they have to be inside, they have to be covered, not to be touched locally by the electron. So when one electron goes by, there is no problem at all. But suppose now I send one electron, and then another electron, and then another electron, and there is no memory, because the potential remains the same. So I expect that after n electron will go by, the thing will grow by square root of n plus minus half h over L. That should be, if there is no memory, then I exchange again and again that amount. So eventually the solid will have to start to move, and that is impossible, because that's against the classical correspondence. There is no force there. So there is a puzzle here. And for a while I was sort of struggling with it, and finally I realized that if perhaps the correct way to think about this random exchange is not an exchange on a line, but an exchange on a circle, then the thing cannot grow. It cannot grow more than just the amount of distance that you can cover on a circle. And then I realized that what is hidden here is an idea of exchange, not of momentum itself, but some periodic function of momentum, like the modulo momentum. Because what are the solenoids doing? They just allow the electron, instead of changing n times h over L, you change n plus half times h over L. You don't know how much momentum the solenoid gave. You only know that they gave momentum modulo h over L, which is equal to half h over L. The modulo variables is you subtract an integer number. If you say that, if you look at what is p modulo p0, it's this function. P modulo p0 as a function of momentum is this function that behaves like this. It's like the time that you see on your watch is the time modulo 12, because each time the time changed by 12, the watch shows the same time. So the idea was then to think perhaps the correct way to describe the interaction between solenoids an electron, which has no classical correspondence, is by exchange not of momentum itself, but of modular momentum. And the first question was, can you write conservation laws that will involve this kind of properties? And the answer is yes, because if you look at the function, periodic function cosine p over p0, which is the same, this thing gives you exactly the same information as the momentum modulo p0 if you write it multiplied by 2 pi. So you see this function has the property that when p changes by integer times p0, the function does not change. So I can look now at the issue, can I write conservation law if there is a collision between two systems and I know that cosine of p1 plus p2 divided by p0 times 2 pi, that is conserved because the sum of the momentum is conserved. So I can open it and write the conservation law as cosine p1 over p0, let me forget about the 2 pi, times cosine of p2 over p0 minus sine p1 over p0 times sine p2 over p0. This is equal to a constant. So let's call cosine p1 over p0 x1. So I have an equation here, x1, x2, minus the square root of 1 minus x1 squared. The square root of 1 minus x2 squared is equal to a constant. You bring this to the other side and take the square of it, and you find an equation. Let's do it. You see the x1 square, x2 square cancels, and you find an equation for an ellipse. So in fact, we see now that we can write the interaction between solenoids and electron in this language, that we have two conserved quantities, cosine p1, say for the solenoid, and cosine p2 for the electron. We have an ellipse here, some kind of ellipse like this, and we know that if the modulo momentum for the electron has changed, that was due to an exchange of this kind of quantities between the two of them. It's not an exchange of a sum, it's an exchange of a product. What is invariant here is the product. But anyhow, if I start initially, say, knowing what is the value of each one of them here, I will know that if one of them changed to this location, then I know what happened to the other one. So instead of having just a conservation law on a straight line, I have now a conservation law for this modulo type of variables. And I claim that this will describe correctly the interaction that happens non-locally. Now, together with this comes another interesting point, and that is the fact that with the aid of this kind of quantities, I can describe the uncertainty principle in a new way. Instead of the uncertainty principle being a quantitative property, I will show that it is a qualitative property. And then once you see that it's a qualitative property, you can ask the question, why does it happen? So here's the idea. If you know that the particle is confined to be inside the box, or inside a box of length L in some direction. So the wave function can be anything here inside. The usual uncertainty principle, if this is x, is written that delta px must be larger or equal to h over L if I know that delta x is smaller or equal to L. So this is a quantitative uncertainty. Let me show you that there is a qualitative uncertainty, and that is that if you look at px modulo p0, where p0 is h over L, then this must be completely uncertain. And how do I show that? If I look at cosine p over p0 times 2 pi and call it cosine of theta of p, something behaves like an angle. Then to say that this is completely uncertain, is to say that the probability to find any theta of p is equal to a constant. So that means that the integral of the probability of theta, of this theta, times e to the I n theta must be equal to 0 for n different from 0. That's the condition that the theta is completely uncertain. Let's see that this works indeed here. If I take the average.
Can you change the marker?
What?
Can you change the marker? It's not clear.
Ah, okay. if I calculate the average of e to the I and theta, which is the same as the average, eraser, what did I do? Here. This is the same as the average of e to the I n p over p0, which is the same as pl over h bar. Then I claim that this is equal to 0. Why? Because when I apply this operator to this state, it takes it away from here by a distance n times L, and there is no overlap between them. That means that the average of this for any n different from 0 is equal to 0, which means now that I can say that there is a new way to look at the uncertainty principle by saying not that this is a quantitative statement, but that the modulo variable must be completely uncertain when I know that the thing is confined to a given L. So now I say that together with this and the other understanding, I can now think of a new way to understand the two-slit experiment, or in general, the interference phenomena. You know, this is the thing that Feynman said, nobody will ever understand it, so I plan to differ with him, and I want to convince you now that there is a new way to think about the interference once you learn to look in this way on the quantum dynamics of interference. And here it is. Suppose I look at the two-slit, the famous two-slit paradox. What is this two-slit paradox? We say we send one electron or one particle after the other, and we see that we get interference pattern, and we see that there is places where we get 0 if the two of them are open, but if each one of them separate is open, it's not 0 there. So the question is how, if each electron or each particle comes by and goes through one slit, how does it know that the other slit is open, right? If we think about it as waves moving here, the waves are not something real. We know that these waves are just probability waves. We don't know what it means to say that probability waves is moving in space. This is not a real picture. The real picture is to think about some electron or some particle that goes through one slit or through the other slit, and somehow, in some mysterious way, it knows that if it goes through one slit, the other slit is open or closed, because it has to behave differently if the other slit is open or closed. And now, we found out, by looking at the interaction between the solenoid and the electron, that there is a non-local exchange that happens between them that depends on the modulo variables. Maybe I will stop here for a minute and explain to you how we see that this is a non-local exchange. Let us look what happened. Indeed, there is a solenoid here, and the electron is moving. Now, suppose the electron, first of all, is described by a wave packet. It moves only on one side. And we say that in that case, there is nothing happens to the electron. That means that the electron behaves freely, like a free particle. What does it mean that the electron behaves like a free particle? It means that if, for example, its velocity was definite, then a free particle means that the velocity does not change. If the velocity is not definite because it's a wave packet, it means that the probability of the velocity is not a function of time. That is the condition, a necessary and sufficient condition, that the particle behaves freely. So we know that if the particle is moving here, its velocity probability does not change. Its momentum probability may change. If, for example, I put here some vector potential, I will see that the momentum change. But if I look at the gauge invariant quantity, which is the momentum minus E over Ca in any direction, that thing does not change. So the probability of the velocity when the electron moving on this side does not change at all. Similarly, if the electron is moving on the other side, here, we calculate the probability of the velocity. It does not change also. What happens if we take a superposition of the two? Then if we connect a line like this and we look at the velocity in this direction, we find out that just when the line is crossing this place where the solenoid is here, that's when the probability of the velocity does change. And then afterwards, it remains constant again. So there is a non-local interaction between the electron and the solenoid, and we ask, what is this non-local interaction? It turns out that this is an interaction that changes the modulo momentum P modulo H over L. Because if I calculate the time the average of e to the I PL over H between the superposition of these two wave packets, then if I change the relative phase, I change this quantity. So I'm saying that we can describe then the interaction between the solenoid and the electron as a non-local exchange of this type of modulo variables. So now let's come back to the mystery of two-slit interference. The idea that I have now is to describe it in the following way. I will say that if I know that the electron moves here, classically that electron will not mind at all if that slit here is open or closed. But for quantum particle, what is relevant is the modulo of the momentum, and the modulo momentum will know whether this thing is open or not, because the equation of motion for the modulo momentum are non-local. On the other hand, I immediately run into the problem of causality, because if I'm saying that the modular momentum changes due to the effect of something that happens far away, if I could test it, I would violate causality. So quantum mechanics saves me by saying that under this condition that you could violate causality, that thing that is exchanged non-locally is completely uncertain. Not quantitative, but qualitatively. That means that I can explain now the uncertainty as coming from a deeper axiom. The deeper axiom is that there could be in quantum mechanics non-local phenomena, non-local effects, and it should still preserve causality. And the only way that this could happen is if I have uncertainty that are complete uncertainty, so that I can't follow this violation of causality. On the other hand, if I know that the electron moves in a superposition of either here or here, then I can say that under this condition, if the electron moves here, it knows that this slit is open. If it moves here, it knows that this slit is open. But now, I cannot violate causality if I will say that under this condition, I can actually observe the change in the modulo variables. So there is now a way to understand intuitively the thing that everybody told us, including Feynman, that we could never understand it. I don't need to talk about a wave that moves here, a mysterious wave that nobody understands what it is. It's a relative probability wave. I don't know what it means to say that probability wave is moving in space. On the other hand, I can think intuitively of a picture that I'm saying that the difference between classical and quantum mechanics is that in classical, all the equations of motion are local. In quantum mechanics, if I replace Poisson bracket by commutator, I can see that the equations of motion are non-local. The variables, by the way, that I exchange non-locally don't have a classical correspondence, because if I look at cosinus PL over H bar, and I look at the limit when I keep L fixed and H bar goes to 0 to go to the classical limit, indeed this is still exchanged non-locally, but this quantity becomes completely wild and I can never see it. So that's why I don't see this non-locality in the classical limit. So I repeat myself. I am saying that I have now an intuitive picture to understand interference by saying that when a particle moves in two slits, it always goes through one slit or the other slit, but it knows which the slits through which it did not go, whether it's open or not, because there are non-local equations of motion. So to summarize, first of all, the topological effect taught me, through this paradox that I showed you, that I should think about non-local equations in quantum mechanics as exchange of modular variables. These modular variables are completely uncertain under condition that I could violate causality, and therefore I can allow non-local interactions and still have causality safe. Thank you very much. There is a question there, yeah.
I don't have a question, I just have a comment.
Okay.
Which is, I don't see why, I mean, everything you've done is really correct, but I don't see why you find a description, refinement, something else.
Yes.
If you want to force yourself to read classically, you have to say, which I've done all the time. And there is in quantum mechanics is introduced that way, as opposed to introducing it in a more intuitive way, by considering that way is horribly non-intuitive.
Okay,
of the pattern is easy generalization to relativistic system.
no, there is easier. Okay, two things. First of all, there is easy realization to this also because I can write a relativistic. I can write a relativistic. Yeah. I can write a relativistic e to the I p mu L mu over h bar, so it's relativistic. That's no problem. Yeah. Okay. All right. Now. But as far as your other question, I mean, your other comment, I will answer you first of all that Feynman, your hero, that knew that knew about path integral, nevertheless said that even though he understands path integral, he still thinks that the two-slit experiment is a mystery and that nobody will ever understand it. So you either
I would love to contradict everyone, including myself.
okay.
He also said that the quantum electrodynamics field theory is all wrong.
Well, okay.
Generalization is sweeping the pulse under the rug.
I agree with you that it's a question of it's.
was right.
No. Wait, please, Pavel. Okay, I agree with you. There's somewhat a question of taste. Okay, my taste is that I feel that that integrating this summing over infinite number of paths is a very nice tool, but I don't understand what it really means because it doesn't mean that the electron really goes on all these paths, right? Because if you try to think how one electron can go through infinite number of passes, including all the discontinuous ones, and no, this. What? Okay. No, mathematically it works, but it's not intuitive. To me, the other thing is more intuitive, but at least you have to admit that we have another alternative. That suggests that there could be another alternative to think, and then everybody can develop his own intuition. I can show you how is this intuition. You can come to many other interesting questions that you could not come from the other thing. Although I like very much the path integral. In fact, I wrote a very interesting article. What is the meaning of a Feynman individual path? Do you know about this article? It's a very, very nice article that explained the first time why Feynman was right and not Bohr when I told him that he was.
Yakir, I have a question and not a comment. I usually comment. The question is,
You already made a comment now also.
it's so beautiful, and it looks like you have exponents, momentum always enters in exponents. Now, there is a thing called Weyl representation.
Yes.
And it was actually introduced.
Oh, you're starting to make comments. What's the question? Yeah.
The question is,
Yes.
there are situations, there should be quantum mechanical situations in which a moment of P and the power of P
Yeah.
would not exist.
Yeah. This is the yeah.
The underlying reason
Okay.
for introducing this is it correct?
Right. So thank you for reminding me that point. You see, if you may think that if you look at I told you that if you look at the superposition of two wave packets, or maybe I did not tell you, if you look at the superposition of two wave packets that have no overlap between them, and you ask what is the thing, what kind of physical variable will know about the relative phase between them, I think Tirza Kaufer talked about it here, then you can show that, or maybe Jeff Tolakson. Anyhow, you can show that if you look at all the moments of momentum and position, you take the average of all of them, none of them will be sensitive to the relative phase. On the other hand, if you look at the operator e to the I PL over h bar, where L is this thing, that average will know about the relative phase. And the question is, how come I can take this operator and expand it with power series of momentum, and what's going on? You tell me that each momentum separately, each power doesn't know it, but this knows it. So this is an example where you have that the sum of Pn, the average of the sum of Pn is not equal to the sum of the averages of Pn, because this thing does not converge, since there cannot be a Taylor expansion for a function which is not analytic. So so the situation exactly that interests us when we have more than one wave packet is exactly that situation, that the usual intuition that we get about quantum mechanics from moments of momentum is not, which correspond to classical ideas, that does not work here. Here we need to go to a new variable, which is this modular momentum, And that is the thing that grasp what is really new in the situation of interference. And that thing has non-local equations of motion, and that's what is new in quantum mechanics compared to classical physics.
Yeah, what would you do if the two states were not symmetric? There would be two different.
No, so there is still, for example, if I have one wave packet like this and another wave packet like this, if they're completely orthogonal, then they will never interfere. But if there is some overlap, when I take this one by distance L to this, there is some overlap, I will get the average of that different from 0. Then I will displace it by a different distance and collect P modulo H over L, P modulo H. I have to take the Fourier transform of the probability of the momentum. And if I take the Fourier transform with all Fourier components, then I get the whole information for the relative phase. Okay?
Okay, well, as I anticipated, you did not overlap with the talk of the professor.
Ah, yeah, okay.
Thank you